Good morning, ladies and gentlemen. My name is Jialuo, and I'm the Assistant Director of the National Center for Transportation Infrastructure Durability and Life Extension. So today I'd like to talk about the mixed design of sustainable nano-engineered high-performance concrete, short for nHPC overlay, for the concrete bridge decks in cold regions. So here's the table of content. I will begin with the background introduction and the objectives of our study, and then provide some detailed procedure of mixed design, and finally do some comparison and conclude my presentation. So what is concrete bridge deck overlay? For a concrete bridge structures in cold regions, the bridge deck can be easily deteriorated by multiple factors such as traffic load, freeze-thaw cycles, or the chemical and physical attack from de-icing chemicals. So instead of replacing the whole full depth bridge deck, applying an overlay on the top of the deteriorated bridge deck will be a more cost-effective option. So here are multiple types of overlay, and for the concrete-based overlay, usually it has a lower water-to-cement ratio for featuring a denser microstructure and a lower permeability to the water and other deleterious ions. But right now, UHPC overlay is becoming increasingly popular throughout the USA, and even though the UHPC overlay features superior properties, we still need to be very careful of all these potential causes that lead to the UHPC overlay to crack from time to time. According to FHWA, UHPC is a cementitious composite material having a typical 28-day compressive strength greater than 150 megapascal after heat curing, or 120 megapascal under standard curing. As we can see here, I plotted the compressive strength of UHPC and high-performance concrete with respect to water-to-binder ratio. And if we can see here, there's an obvious gap between these two categories. And if we regard the UHPC with a cement content less than 80% by the weight of total binder, we may find that people may prefer to decrease the water-to-binder ratio to achieve even higher compressive strength. However, for concrete bridge deck overlay, such high compressive strength is over-designed, and our target is to fill this gap by developing a sustainable and environmental friendly and cost competitive nano-engineered high-performance concrete. So we employed a stepwise method for our mixed design. The first step is to determine the binder combination, not only with the incorporation of supplementary cementitious materials, but also the nano-montmorillonite, also known as nano-clay. And then we're going to move on to determine the water-to-binder ratio by the 28-day compressive strength of the paste. And then we will optimize the sand gradation of the mixture by employing a packing model. After that, we will determine the volume fraction of the binder phase and the sand phase. Finally, we will determine the fiber content of our mixture. So the first thing of step one is to narrow down the range of SCMs in nHPC, our nHPC binder, which employs the UHPC binder as a base and multiple types of SCMs in it. The UHPC binder in our study has a fixed amount of type 1-2 Portland cement, Class C fly ash, and silica fume, and limestone powder and Class F fly ash will be used as the SCMs. So we have the table of the group that we are going to first narrow down the range. The maximum substitution of the SCMs of limestone powder and Class F fly ash is 20%. And we're going to do the mini slump test to determine the linear relation between the relative flow and the water to binder ratio. As you know, the slope is RWD, which is short for relative water demand, and the intercept is known as minimum water content. So by testing the fresh mixture with a preliminary water to binder ratio of 0.24, we can see that the MWC of limestone powder, the optimum range of limestone powder is from 5 to 10%, because a low MWC indicates a high packing density of the binder system, and a high RWD value indicates that the binder system is more robust to the change of the water to binder ratio. Similarly, we can find the optimal range of fly ash class F fly ash is 10 to 15%, and in the ternary binder system, the results confirm that the limestone powder content should be less than or equal to the fly ash. And the preliminary range for the nano clay is from 0 to 2.5. And now we can optimize our binder by the central composite design method. As you can see, we have 20 runs in this table, and with 4 nanoclay content. As you all know, that the dispersion of nanoclay in the cement paste can significantly affect the compressive strength. So we need to first to determine the best dispersion time for the via ultrasonic dispersion for the nanoclay. So we use the wrong one, which has a 1.25% nanoclay content, and with a preliminary water to binder ratio of 0.24, and a fixed amount of high range water reduced in the mixture to test the flow diameter of the fresh mixture, so that the optimum dispersion time of the nanoclay can be determined. We investigated 3 types of nanoclay, and as you can see, the results on the left hand side, we will select the PT nanoclay as our nanoclay, and then the best dispersion time is 40 minutes for the nanoclay content of 1.25%. So if you remember that we have four nanoclay content, we can similarly do the same test to obtain the best dispersion time for each content of nanoclay. So now we can optimize the nHPC binder combination. As we can see here, with the increase of the nanoclay content, the compressive strength will decrease, while the demand for high range water reduced in the mixture will first decrease and then increase. So with the help of design expert software, we can come up with the optimal binder combination of this number. Now we're going to move on to step 2, which is determine the water to binder ratio. So we will use the obtained optimal binder combination and with various water to binder ratio to test their 28-day compressive strength and demand of water, high range water reduced in the mixture to achieve the flow diameter of 280 plus minus 10 millimeter. So according to the result, we can say that the optimal water to binder ratio is 0.24. Okay, so for the optimized sand gradation, we will employ the modified Anderson model to achieve the optimal sand gradation curve. We do the sieve analysis of most of the sands available on the market, but they look much finer than this curve. So we find that that is pretty difficult to simply blending sands from different sources to achieve our desired sand. So finally, we decide to sieve the sand first and then blend the sand with the exact percentage at each gradation to have the sand with desired sand gradation curve. So with the sand and binder ready, we can determine the volume fraction of each phase. For the binder phase, actually we can separate it into two parts. The V void part accounts for the paste for filling the voids among the sand particles, while the VEXP part means that the excess paste for lubricating. Here are the two equations for each term, and RSA is a coefficient that related to the shape and angularity of sand based on our visual observation. We determine it as 3. And here's the equation for the sand phase. So after doing the ASTM C29 and C128 tests, we can obtain the bulk density and density of the blended sand so that the void ratio can be determined. And then we obtain the minimum value for the VB over VS ratio of 0.6. However, if we directly employ such a minimum value of this ratio, we can find that the mixture will show some slight bleeding when we try to achieve the flow diameter of 280, and the best we can do is only 252. So we start from 0.7 of the ratio of VB over VS to 1.9, and the optimum ratio of VB over VS is determined to be 1 according to the compressive strength and demand for high range water reducing in the mixture. So here's the final step. Here are some basic information of the steel fiber and PE fiber that we used in our study. And the first thing that we try to do is to determine the upper limit of the fiber content. As you can see, the upper limit is 1.5% by volume for the steel fiber and 0.2% by volume for PE fiber. So here's the results. We also did the test of 28-day and 7-day compressive strength and the demand of higher range water reducing the mixture. Further, we did the flexural performance evaluation on these nHPC samples with various fiber content. As we can see here, steel fiber gives the nHPC sample strength hardening after the first crack, while the PE fiber doesn't. And also, we can see that the tensile strength of the nHPC fiber and nHPC sample with the combo of steel fiber and PE fiber has only half of the post-cracking tensile strength with respect to the nHPC sample with steel fibers only. So here's the detailed results. And the optimum fiber content can be determined as 0.5% of steel fiber. So here's the complete mix design of our nHPC, and we can do some comparison with the innovative lightweight UHPC thing in terms of cost or energy consumption. And also we do the strength normalized cost and strength normalized energy consumption. As we can see, the price is pretty competitive and also with less energy consumption, which means smaller carbon footprint. So now I would like to conclude my presentation. We developed a sustainable and environmentally friendly nano-engineered high-performance concrete mixture for the application as the overlay of concrete on concrete bridge decks. And for the application of nanomaterials, especially the nanoclay in cementitious mixtures, it needs the preliminary investigation to obtain the optimal or the best ultrasonic dispersion parameter, like the dispersion time, so that the nanomaterials can be well dispersed in the system. And finally, in terms of cost and energy consumption, nHPC is approximately 25 to 50% lower than that of UHPC. But further durability experiments are necessary to evaluate the application of this product in the field. And thank you very much. Please feel free to contact me or